Southampton, 1931. The tide was low along the River Itchen, and inside the Supermarine workshops a small crowd gathered around a sleek metal prototype resting on its trestles. The machine looked nothing like the biplanes dominating British airfields. Its wings seemed carved rather than assembled, its curves unusually clean, its structure almost arrogant in its simplicity. While visitors studied its unfamiliar shape, one man watched it with a different kind of intensity. R.J. Mitchell wasn't admiring a prototype. He was evaluating a future that few around him had even begun to imagine. Mitchell had already demonstrated that he understood speed better than most engineers of his generation. His seaplanes for the Schneider Trophy had torn across the water at record-breaking velocities, proving that aerodynamic discipline could defy expectations when applied without compromise. He learned early that even minor imperfections, a misaligned rivet, a poorly managed airflow transition, an unnecessary gram of weight, could turn victory into failure. These lessons shaped everything he designed, and by the early 1930s, Britain needed that mindset more urgently than ever. Aviation was shifting from wood and canvas biology to metal and engine physics. The next war would not wait for designers to catch up. Mitchell knew this long before the Air Ministry did. He was not an engineer who made decisions by instinct or emotion. To him, aircraft were problems expressed in 3 dimensions. A line drawn on a blueprint had consequences at full throttle. A small change in curvature altered lift distribution across an entire wing. A fraction of a degree in incidence made the difference between stability and disaster. Mitchell studied these relationships with the precision of a mathematician and the stubbornness of a craftsman who refused to accept good enough. He kept notebooks filled with airflow sketches, structural calculations, and handwritten annotations that revealed the mind of a man who trusted data more than promises. He wasn't trying to outdesign other engineers. He was trying to outdesign the war he saw forming beyond the horizon. As tensions across Europe grew, the Air Ministry issued a requirement for a new kind of fighter aircraft. Faster, stronger, able to climb rapidly, carrying sufficient firepower to challenge whatever Germany might produce. Many designers responded with conservative ideas, refining biplane concepts or proposing incremental improvements. Mitchell instead chose to rethink the basic geometry of the modern fighter. He studied low-drag fuselage forms, thin cantilever wings, retractable landing gear, and stressed skin construction. No single element was revolutionary on its own, but the combination hinted at a leap that Britain had never attempted in a military aircraft. Mitchell's early sketches showed wings that curved with deliberate precision, a fuselage tapering smoothly around its engine, and structural elements distributed to minimize unnecessary mass. He was obsessed with airflow behavior at high speeds. He understood that drag was the enemy of performance, and his approach focused on eliminating every surface that didn't contribute directly to lift, stability, or cooling. He often arrived at the factory before sunrise, reviewing test results and making adjustments that seemed microscopic to casual observers, but transformed handling during flight. Draftsmen described him as calm, focused, and methodical. A man who believed that an aircraft should express mathematical harmony when viewed from any angle. Even at this early stage, Mitchell sensed that Britain would need an aircraft capable of rising quickly into the path of incoming bombers, engaging escort fighters, and returning home with enough strength left to fight again the next day. Speed alone wasn't enough. The design needed structural honesty, the ability to withstand combat stress without sacrificing aerodynamic purity. Mitchell experimented with monocoque fuselage construction, new wing spars, and layouts intended to support heavy armament, without destabilizing the aircraft's center of gravity. Every refinement brought him closer to a fighter that could change the balance of power in European airspace. Inside Supermarine, engineers began to notice that Mitchell's blueprints had a coherence absent from many contemporary designs. His aircraft didn't blend features from various sources. They evolved logically from the physics he studied. When a test revealed a flaw, he corrected the geometry directly rather than compensating with patches or external additions. His aircraft weren't built through compromise. They were built through deliberate choice. This commitment to clarity would soon evolve into a machine that captured the attention of the Air Ministry, the Type 300, the first true ancestor of the Spitfire. But Mitchell also understood the cost of innovation. Every improvement meant new structural challenges, new stress calculations, and tighter margins for error. His team worked under pressure, refining the prototype while external events accelerated. Germany was rearming, and British intelligence warned of fighters and bombers designed with increasing sophistication. Time was becoming a resource Britain could not replace. Mitchell pushed forward, balancing ambition with discipline, knowing that a future conflict would be decided in minutes of combat, shaped by years of engineering. As the final lines of the Type 300 took form, one question defined the next stage of his work. Could Mitchell's pursuit of aerodynamic precision deliver an aircraft capable of meeting the war Britain feared was coming? What breakthrough would transform his promising prototype into the fighter that would carry Britain through its darkest hour? Work on the Type 300 advanced rapidly, but the prototype still existed only as a sequence of evolving blueprints, stress diagrams, and airflow studies pinned across Mitchell's office walls. He knew the concept was promising, yet promise alone would not convince the Air Ministry. Britain was in a transitional moment. Older aircraft were becoming obsolete overnight, and new designs carried risks that frightened conservative planners. For Mitchell to move the Type 300 from theory to reality, he needed to refine every aspect of the design until its purpose became undeniable. His first focus was the wing. Most European fighters relied on thick, straight-edged designs that offered stability but sacrificed speed. Mitchell approached the problem differently. He shaped the wing like a curve drawn in a single uninterrupted motion, its thickness tapering smoothly from root to tip. This elliptical form was not aesthetic, it was mathematical. It reduced induced drag, distributed lift more evenly, and allowed the aircraft to maneuver without the abrupt stalls common in many fighters of the era. Engineers studying the drawings initially questioned the practicality of producing such shapes, but wind tunnel tests confirmed that Mitchell's instinct was correct. The design promised higher efficiency during tight turns and reduced resistance during high-speed flight, giving the prototype a performance advantage before a single engine ever turned. Next came the challenge of housing the power plant. The new Rolls-Royce Merlin engine offered extraordinary potential, but integrating it into a fighter airframe was complex. Cooling, vibration, airflow intake, and weight distribution had to work in perfect harmony. Mitchell studied airflow charts around the engine block, observing how pressure fields shifted, with minor changes to the cowling's curvature. He adjusted the lines of the fuselage repeatedly, ensuring that the Merlin's power translated into usable speed rather than wasted turbulence. His design integrated the engine with an almost organic simplicity, reducing drag at the nose and creating a smooth transition into the aircraft's body. Mitchell also recognized that speed without firepower was meaningless. The Air Ministry required 8 machine guns mounted in the wings, a configuration that imposed both structural and aerodynamic complications. Mounting the guns too close to the fuselage risked destabilizing recoil forces. Placing them too far outboard invited wing flex issues. Mitchell calculated the precise points where the wing spar could support the weight without compromising rigidity. The gun ports were aligned along airflow paths, optimized to prevent excessive drag. Even the placement of ammunition boxes was evaluated meticulously, with diagrams mapping how weight would shift as rounds were expended during combat. While the technical work intensified, the broader environment around Supermarine grew increasingly urgent. Intelligence reports indicated that Germany was producing fighters with advanced engines and all-metal airframes. No one yet knew the capabilities of the Bf 109, but rumours alone were enough to accelerate design timelines. Mitchell responded by tightening the development cycle. Test components were fabricated quickly and inspected with uncompromising standards. Structural frames were assembled and disassembled repeatedly, as material limits were studied in detail. He tracked how each adjustment influenced the aircraft's centre of gravity, lift characteristics, and stress distribution during high-load manoeuvres. Despite the pressure, Mitchell avoided shortcuts. His approach was systematic, grounded in evidence rather than speculation. When a design question emerged, he consulted wind tunnel data, structural tests, and engine performance charts until the answer revealed itself through numbers rather than opinion. Draftsmen recalled that he often worked late into the night, pencil marks accumulating across revised drawings until the geometry reached a state he considered honest. He used that word often to describe an aircraft whose structural logic was free of contradiction. As the prototype neared approval, Mitchell understood that innovation alone would not secure the Air Ministry's support. He needed to demonstrate that the aircraft could be manufactured efficiently and maintained under operational strain. He reviewed rivet patterns, simplified access panels, and optimized the internal structure for rapid repair. Engineers analyzed stress concentrations at key joints, reinforcing them without adding unnecessary weight. Mitchell believed that a fighter's performance meant little if it could not withstand repeated sorties and absorb battle damage without catastrophic failure. The Type 300 was designed not only to excel in controlled tests, but to survive the unpredictable reality of war. By mid-1934, the aircraft's design reached a level of coherence that impressed even skeptical officials. The Air Ministry recognised that the prototype represented more than incremental progress. It was a leap into a new generation of fighter architecture. The combination of the Merlin engine, the elliptical wing, and Mitchell's aerodynamic refinements produced a profile unmatched by anything currently flying under British colours. Approval for the first prototype was granted, marking a turning point in the project. Construction began soon after, and momentum shifted from theoretical perfection to practical engineering. Frames were assembled on the workshop floor. Sheets of metal were shaped and riveted into position. The curve of the wing, once a debated concept, became a tangible structure stretching across the hangar. Mitchell supervised every stage, observing the alignment of spars, inspecting control surfaces, and confirming that the manufactured components remained faithful to his calculations. The Type 300 was no longer an idea. It was becoming a physical machine, capable of challenging the emerging threats across Europe. Yet, even as the aircraft took shape, Mitchell knew the greatest tests still lay ahead. Once it entered the air, every assumption, every calculation, and every decision would face scrutiny from the unforgiving physics of flight. What challenges would the prototype encounter once it lifted from the runway and met the sky for the first time? The first prototype of the Type 300 rolled out onto the tarmac, with a sense of anticipation that spread across the Supermarine team. For months, the design had lived only in diagrams, airflow charts, and Mitchell's relentlessly revised sketches. Now the machine stood under its own weight, metal skin shimmering under the morning light, its elliptical wings stretching outward, like a promise waiting to be tested. The moment the wheels touched the runway for trials, engineering moved from theory into the unforgiving realm of flight. Early tests revealed exactly why Mitchell refused to rely on instinct alone. The aircraft demonstrated impressive speed, but handling required refinement. Control forces at high velocity felt heavier than predicted, and airflow separation along the wing routes appeared earlier than wind tunnel data suggested. Pilots reported that the aircraft climbed quickly but demanded precise inputs to maintain stability during tight turns. For Mitchell, none of this was discouraging. Flight testing was the natural extension of design. the moment where numbers met reality. He returned to the workshop with renewed focus, revising control linkages, adjusting aileron balance, and narrowing gaps between surfaces to eliminate unnecessary turbulence. The Merlin engine brought its own set of challenges. Its power was essential, but heat build-up during extended climbs threatened to compromise performance. Mitchell studied temperature profiles across the fuselage, working with Rolls-Royce to reshape coolant inlets and reposition radiators to maintain efficiency without adding drag. The famous underwing radiator bath, later recognized as a hallmark of the Spitfire's silhouette, evolved from these experiments. Its shape balanced cooling requirements with aerodynamic cleanliness, turning a functional necessity into a performance advantage. Each test flight returned with new data. Engineers charted vibration frequencies, stress variations across the wing spars, and pressure differentials along the fuselage. Mitchell checked every curve against his original models. When discrepancies appeared, he traced the source with methodical patience. A slight flutter at high speed led to adjustments in trailing edge stiffness. A minor yaw tendency during rapid throttle changes triggered a re-evaluation of tail geometry. Progress was measured not in dramatic breakthroughs, but in steady, disciplined refinement, the process that defined all of Mitchell's most successful designs. As the prototype matured, political urgency intensified. Reports from the continent indicated that Germany had fielded the Messerschmitt Bf 109, a fighter with advanced aerodynamics and a powerful inline engine. Britain needed a competitor, and it needed it quickly. The Air Ministry monitored the Type 300's progress with growing interest, pushing for accelerated development without sacrificing reliability. Mitchell understood the pressure but refused to compromise. Structural integrity for speed. A fighter that excelled on paper yet failed under operational strain would serve no purpose. His aim was not to surpass the enemy for a few months. It was to give Britain a design that could evolve throughout the war. Throughout this critical period, Mitchell's health began to deteriorate. A diagnosis he had kept private from most colleagues now cast a shadow over his work. Pain made long hours more demanding, yet he continued to oversee tests, review engineering revisions, and guide every refinement. Colleagues recalled that he moved more slowly but with the same intensity in his eyes. Engineering was not simply his profession. It was the structure through which he viewed the world, and the Type 300 had become the culmination of that vision. Even as treatment and fatigue limited him, his presence in the workshop remained constant. The aircraft improved with each iteration. Its turn performance sharpened, its climb rate increased, and its high-speed behaviour stabilised. Mitchell focused particularly on the harmony between engine, wing, and control surfaces, a triad he believed defined all great fighters. Test pilots began reporting impressions that hinted at something rare, a machine that was not only fast, but intuitive, responsive, almost instinctive to fly. Mitchell viewed these comments cautiously. He preferred numbers to impressions, but the emerging picture aligned with his predictions. The design was reaching a point of equilibrium where aerodynamic efficiency and mechanical reliability supported one another instead of competing. As final modifications were completed, Supermarine prepared for official trials. The Type 300 faced assessments that measured structural strength, agility, stability under various loadouts, and high-altitude performance. Mitchell observed from the sidelines, watching the aircraft he had shaped through years of disciplined work rise into the sky with purpose. Trials confirmed what his calculations had suggested. The prototype exhibited exceptional potential. It accelerated cleanly, maintained energy in sustained climbs, and delivered firing stability superior to competing British designs. Yet for Mitchell, success was not defined by tests alone. He evaluated the aircraft's ability to adapt to future improvements. Could the airframe accept new engines? Could the wing structure support increased armament? Could the fuselage handle rapid manufacturing under wartime conditions? These questions mattered as much as raw performance. Britain needed a fighter that would not only win the opening battles, but continue evolving as the conflict escalated. The Type 300 offered that flexibility. As approval moved closer, the true transition began. The prototype would soon leave the stage of concept validation and enter the demanding world of full-scale production. Factories, supply lines, material planning, and workforce expansion would now determine the aircraft's future. Mitchell, aware that his health was fading, accelerated his efforts to finalize design choices and document every critical parameter. The fighter that would soon be known as the Spitfire was ready to move beyond the drawing board and onto the assembly lines of Britain. But a decisive question remained. Would this aircraft, forged through precision, discipline, and relentless refinement, meet the unforgiving test of a war now approaching Britain's doorstep? When the first production models of the Spitfire left the lines at Supermarine, Britain stood on the threshold of a conflict that would test every assumption behind Mitchell's work. The aircraft entered service quietly, with no grand announcements and no immediate recognition of the role it was destined to play. Pilots trained, ground crews adapted to the new structure, and engineers studied how the machine behaved under operational strain. But as tension thickened across Europe and war finally erupted, the Spitfire's true value began to emerge. Germany's fighters were fast, aggressive, and supported by a doctrine built for rapid domination. Britain needed a machine capable of meeting that challenge head-on, and Mitchell's design prepared the RAF in ways few fully understood. The Spitfire distinguished itself first not by raw speed, but by the precision of its aerodynamic balance. Pilots discovered that the elliptical wing delivered a turning performance unmatched by contemporary fighters. Whereas many aircraft lost stability during aggressive maneuvers, the Spitfire maintained control, allowing skilled pilots to dictate the geometry of combat. Energy retention during climbs proved exceptional, enabling rapid altitude changes that determined life or death in aerial engagements. These traits were not accidental. They were the direct result of Mitchell's disciplined approach. The wing's geometry, the fuselage's curvature, and the distribution of internal structure converged to create a fighter that translated theoretical predictions into battlefield advantage. As the Luftwaffe advanced through Western Europe, news of the Bf 109's combat effectiveness spread quickly. German fighters dominated the skies over Poland and France, and many analysts feared that Britain would face the same fate. But when British and German aircraft finally met over the Channel, the RAF discovered that the Spitfire could match the Bf 109 in speed and surpass it in manoeuvrability. The Merlin engine provided strong acceleration, while the aircraft's aerodynamic purity allowed pilots to hold tighter turns and recover energy more efficiently. Even the visibility from the cockpit, something Mitchell had refined through careful shaping of the canopy and fuselage, gave pilots an edge during fast-paced engagements. Combat confirmed what wind tunnels and calculations had suggested. Mitchell's fighter operated as a coherent whole, each component supporting the others with rare consistency. But the Spitfire's impact extended beyond one-against-one encounters. Its structure proved resilient under stress, allowing ground crews to repair damage quickly and return aircraft to service. The airframe accommodated incremental modifications without losing performance, enabling engineers to introduce new radiators, armament adjustments, and engine upgrades as the war evolved. This adaptability was critical. Germany refined its aircraft continuously, and the RAF needed a platform capable of matching that pace. Mitchell had not lived to see the war unfold, but his insistence on structural honesty, designing an airframe that could withstand refinement rather than break under it, ensured that the Spitfire remained competitive through every phase of the conflict. During the Battle of Britain, the world witnessed the full weight of Mitchell's achievement. German bombers swept across the Channel with fighter escorts designed to overwhelm British defences. Yet the Spitfire's climb rate, turn radius, and overall responsiveness allowed RAF pilots to intercept and challenge the enemy before they reached their targets. While the Hurricane bore the bulk of bomber interceptions, the Spitfire neutralised the Bf-109 threat, preventing German fighters from achieving air superiority. The elliptical wing that Mitchell had drawn years earlier became a national symbol of resistance. Its smooth curves, once debated in design rooms, now carried the hopes of a country fighting for survival. As the war progressed, the Spitfire continued to evolve. Engineers introduced more powerful Merlin variants, then later replaced it with the Griffon engine, significantly increasing thrust and high-altitude performance. The airframe absorbed these changes without losing its defining qualities. Wing modifications allowed the installation of cannons, clipped configurations improved roll rate, and reconnaissance versions reached altitudes beyond the reach of enemy fighters. Each iteration reflected Mitchell's original design philosophy: build a fighter with the structural integrity to grow, adapt, and meet challenges unknown at the time of creation. Behind the scenes, engineers often acknowledged that the Spitfire felt engineered with foresight uncommon in military aviation. Mitchell's approach, combining aerodynamic theory, rigorous testing, and an uncompromising pursuit of balance, produced a machine that never stopped being relevant, even as technology accelerated. The RAF eventually deployed Spitfires across multiple theatres, from the Mediterranean to the Pacific, confirming the aircraft's versatility under vastly different conditions. Britain's strategic position improved not only through tactics and training, but because Mitchell had delivered a tool capable of elevating the RAF's operational potential across the entire war. By the time the conflict ended, the Spitfire had earned a place among the most influential aircraft ever built. It did not win the war alone, but it shaped its direction, protected Britain during its most vulnerable moments, and demonstrated how disciplined engineering could alter the trajectory of national survival. Mitchell did not live to see this legacy, yet every sortie flown during the war carried the signature of his work: the precision, the aerodynamic clarity, the refusal to accept compromise. His story is not only about a fighter aircraft, it is about an engineer who transformed principles into power, theory into survival, and geometry into a strategic advantage felt on every front of the conflict. As the war closed and the world entered a new era of aviation, one question framed the memory of his achievement: how would the future of aircraft design continue to be shaped by the principles Mitchell embedded so deeply into the machine that carried Britain through its darkest hour?